last up, we have Jake Rada and Arianna Poles Aldrey. And they, did I butcher that? Yeah, thank you. And your net zero cooling. So forward is here, back is there. Back again.
Yeah. I'll just wait until you get ready. Ready? Yeah. So good afternoon, everybody. My name is Arianna, and this is Jacob, and we're going to present our project on net zero today. So there you go. So to give a little bit of a background, this picture represents basically a comparison on the average temperature of the world between in 1920 to 2017. There is an obvious, it's obvious that there is some global warming. It's more obvious and noticeable in the northern areas. We can see the North Pole, Russia or Asia, but we can also see there is global warming in the equator lines. In the Amazon forest or Africa areas and some of the Asian, in some of the Asian islands. So these areas of the equator are also basically more vulnerable. Why? Because they experience a higher temperature throughout the whole year compared to other countries. These areas also represent a lower income, some of the lower income countries. So this second picture here is a little bit tied to the other one. This basically represents the rising sea level due to this global warming. The darker blue that you can see in the picture is more risk for the population due to this rising sea level. And it also corresponds to some of the Asian islands, Australia, some countries in Africa such as Libya and Egypt, and also some of the South American countries. So now, to bring this a little bit closer to us, this is a map of the United States. What does this map represent? Well, there is something that is called the urban heat island effect. What is the urban heat island effect? Well, it basically represents an increase in the temperatures of the metropolitan areas compared to the ambient temperature. Here we can see that bigger cities have a higher temperature. We can see the New York State, Chicago, or Los Angeles area. So another statistics is within the United States, there are an average of 1,000 people that die due to extreme heat. Can you imagine how much this would be also in equator areas or countries that experience a higher temperatures? So now this is my question. What if we could do this? We could cool these places without using any energy and without damaging the environment.
So I just want to bring up some other solutions that other engineers and architects have tried to implement in other areas of the world. So our first picture on the left is a building in Zimbabwe that is modeled after an anthill. This is supposed to have better airflow, which will make it cooler for the workers throughout the day. Secondly, in our top right, this is in Medina, Saudi Arabia. These are umbrellas that fold out during the hottest portion of the day. And then thirdly, in the bottom right, is the Khalifa Soccer Stadium in Qatar. This is going to be home to the 2022 FIFA World Cup. Now, this has also been specially engineered to be cooled better in, obviously, the extremely hot country of Qatar. But all three of these and many other solutions have the same problems where they're expensive and they're complex and they can have inefficiencies involved during the design. All of these have been specifically made for their area. So we presume that we can have something that you implement anywhere. Our assumption is we can use radiative cooling and implement it in any area that is energy free and cool down our respective volume. So the way this technology works is that it emits heat between the 8 and 13 micrometer wavelength range as infrared radiation directly into space. Simple heat transfer is heat goes from hot to cold, and outer space is at about 3 degrees Kelvin. So obviously there would be a large amount of heat transfer from our surface into outer space. No energy needed. So for a rough timeline, in 2015, Stanford University first reported a very useful use of this technology. We started working on this a year later, and then within a year of our lab working on it, we received about 11 or 12 degrees Celsius drop within our environment. By 2020, we hope to have some industrial level implementations of this design. We have here just a sample design. It's going to be small boxes that you can place on top of your roof. You would connect this to your air conditioning system within inside the building, or it could act as a standalone cooling system. You would be able to have more efficient cooling, more efficient air conditioning, and this would decrease the amount of greenhouse gases used in energy production. So finishing off on costs, we believe with our current technology, we can produce at about $20 per square meter. Given a 100 square meter house, it would be about $2,000 to cover that roof, and averaging out, at least in the United States, about $800 can be saved per family per year. This would give us a greener future and is also a smart solution for our energy needs and cooling. So thank you, everybody.
Nice job. Questions from the judges?
Draw the line for me a little bit more in terms of, we talked about timeline, you talked about obviously the effect climate is having and where it's having that. Draw the line to me about how this really makes a fast dent. We've got 10 years to really get our emissions under control, right? To connect the dots for me on how this is actually going to ramp up and really decrease fossil fuel use. In other words, how much of the percentages is cooling around the world that is, could be taken offline, if you will?
Well, the issue is that we have a growing population, and a growing population also requires growing energy usage. We're obviously trying to get more green energy solutions for this energy generation. But we also want to combat this issue from the other side, where we can implement something. So with our radiative cooling panels, they will be working without having any input energy once they're installed. And once they're installed, they are constantly working. So long as you don't have a cover on it, it will always be emitting heat day and night into the outer space. This will allow us to have more efficient air conditioning, and this more efficient air conditioning systems will require less energy. They'll be utilized better, so therefore it'll be decreasing the total amount of energy used, and this total amount of energy used goes back into an energy generation facility, therefore reducing the amount of either fossil fuels, whether it be coal, oil, whether it be even wind power. That energy generated can be even diverted somewhere else where the load itself is much less in areas that have this technology implemented.
Yeah, and also to give you a little bit of some more statistical data, there is an implementation in a factory of this radiative cooling technology, which the factory was covered by 60% of the factory was covered by this radiative cooling technology, and they managed to have a 21% decrease in the energy usage of the company itself. The good thing about our technology that we really like is, yes, in developed countries, we reduce the amount of energy usage, but also in the not as developed countries, we can help with the decrease of the cooling temperatures and the fact that it's energy free and there is no maintenance. Then it will really help these low-income countries as well.
Thank you.
Right.
How is your design different from the one you just talked about in the factory? So this isn't like a unique idea. This is you taking someone else's idea and making it better?
Well, these are all similar, basically, because it is just we have a panel that would be obviously sending heat out into outer space. What we're trying to do is come up with more efficient and materials that have a better temperature drop than the one that has been reported. The one that has been reported was from 2015 and had only about 7 to 8 degrees Celsius drop, but our lab itself has created a material that has an 11 degrees Celsius temperature drop. So with current trends, we are able to start decreasing the overall temperature drop, or increasing the overall temperature drop from the outside environment itself. So we're working on improving this technology as well.
Right, and also the materials that we are using, compared to other technologies, they're very expensive. Mm-hmm. They are kind of in the semiconductor industry, so which means very technological. But what we are using is very cheap, very affordable, and we hope it can be at least as efficient or more and achieve the same goal. Mm.
Right. Can you use the last minute or however much we have just to help me wrap my brain around exactly what's going on here? So I understood the background, I understand the motivation, all that's very clear, but the technology itself, so can you just tell me exactly how this is working?
Yes, so just going back, hopefully I'm going the right way.
Yes.
So Yeah, so going here, this would probably be the best slide. We have our sun is obviously sending heat down, and within our atmosphere, there are several bands, you can consider them. The most important one is between 8 to 13 micrometers. Within this range, these solar panels will be able to take the incoming wavelengths or waves of light from the sun and send them back out into outer space as infrared radiation. This will allow us to have a temperature drop within whatever volume is below these panels themselves. There's no, like I said, there's no energy needed to perform this heat transfer. Once it is input, it works.
So my last question then is this going to increase heating costs in the winter?
No, because like I said, once you cover it, it can be turned off basically.
Okay, I see.
For example, our implementation, we're cooling down water right now, and we're using that water to pass through the system, just as in lab purposes. But yeah, we have got great results.
All right, great. Thank you.
Yeah.